Good morning, students. Today we will meet with another new topic that is mode theory. And before going to the details of mode theory, let us have a look on what is acceptance angle and what is numerical aperture. And first of all, let me something about acceptance angle. And here there is a figure, and in that an incident ray is showing, and there is a total internally reflected ray, and critical angle theta is also shown. And also it is given that core refractive index is n1 and cladding refractive index is n2, and so we can define the acceptance angle, that is the acceptance angle which is represented by theta a is the maximum angle to the axis of the fiber that light entering the fiber is propagated. That means the acceptance angle is the maximum angle to the axis of the fiber that light entering the fiber is propagated. And the value of the acceptance angle depends upon the fiber properties and transmission conditions. And also the acceptance angle is related to the refractive index of the core and cladding and medium surrounding the fiber. And here we are assuming that the medium surrounding the fiber is air. Suppose it has a refractive index n0. Then the relationship that connecting these refractive indices and acceptance angle gives the numerical aperture. Okay. Next is the numerical aperture, and that relationship that connects the acceptance angle with the numerical aperture is Na is equal to n0 into sine theta a, where theta a is the acceptance angle, Na is the numerical aperture. And the numerical aperture is the measurement of the ability of an optical fiber to capture light. And the numerical aperture of the fiber is represented by Na, and Na is used to measure source to fiber power coupling efficiencies. A high Na indicates a high source to fiber coupling efficiency. So this is all about the numerical aperture. These are terms, sometimes these may be asked for short answers. That is why I am discussing this. And the next is the mode theory. Before going to mode theory, usually the mode theory along with the ray theory is used to describe the propagation of the light along an optical fiber. And mode theory is used to describe the properties of light that ray theory is unable to explain. And the mode theory uses electromagnetic wave behavior to describe the propagation of the light along a fiber. That means mode theory uses electromagnetic behavior to describe the propagation of light along a fiber. A set of guided electromagnetic wave is called the modes of the fiber. So there is difference between ray theory and mode theory. And we are representing, in ray theory we are representing light as a rays, but in the case of mode theory we are representing it as an electromagnetic wave, and we are explaining its characteristics and its propagation based on that electromagnetic wave. So first of all we have a look at the plane wave, and first figure shows the plane wave, and mode theory suggests that the light wave can be represented as a plane wave, and plane wave is described by its direction, amplitude and wavelength of the propagation. A plane wave is a wave whose surfaces are constant phase and it consists of infinite parallel planes, and these planes are normal to the direction of propagation, and it is shown in the first figure. And the planes having same phase are called wavefront, and the wavefront of the plane wave has a wavelength lambda is equal to c by f into n. That is lambda, wavelength of the plane wave is given by lambda is equal to c by f into n, where c is the speed of the light in vacuum and f is the frequency of light, and n is the refractive index of the plane wave medium. So you got the idea about the plane wave. So and in the figure it is given the propagation of light is shown. It is from left to right side, and wavefront is also shown. And the plane wave or wavefronts propagate along the fiber similar to the light rays, and its propagation is also shown in the last figure. And all the wavefronts incident on the fiber at angles less than or equal to the critical angle of the light acceptance propagate along the fiber. So it is shown that there is a wavefront, incident wavefront, it is propagating along the fiber. It is seen that it is totally internally reflected, but you should remember one thing, that all the wavefronts incident on the fiber at angles that is less than critical angle does not propagate along the fiber, and wavefront may undergo a change in phase that prevents the successful transfer of light along the fiber, and wavefronts are required to remain in phase for light to transmitted along the fiber. Okay, you got the idea. And in the case of ray theory, we are saying that once a ray is uh, incidenting on the core, if its angle of incidence is less than the critical angle, it will propagate through inside the core of the fiber. But in the case of wavefront, we cannot say like that. That is because sometimes the wavefront may undergo a phase change. Here it is seen that the incident wavefront is coming from outside, and once it touches the core, it will be refracted, and again it is touching the core cladding interface, again it is reflected back, totally internally reflected back, so its phase will be changing. Actually it is not shown in this figure, but actually what happens is its phase will change. And once that at the point A, the point A is marked here, and in that point A, the wavefront changes its phase, and once it again touches the core cladding interface at the lower portion, and it again reflected, totally internally reflected back, and its phase also changes. Again it enters into the core cladding interface in the upper part, and it is also changing phase. It again changes its phase. So, wavefront may undergo a change in phase that prevents the successful transfer of light along the fiber. And wavefronts are required to remain in phase for light to transmitted along the fiber. And consider a wavefronts are required to. What is the point is that wavefronts are required to remain in phase for light to be transmitted along the fiber. And in the figure also it is showing that it is changing the phase. Actually it is not clearly seen on the figure, and the wavefront undergoes a gradual change as it travels down the fiber in the lower figure, and the wavefront must remain in phase after the wavefront transverses the fiber twice and is reflected twice. That means here it is saying that it is reflected at the first point, and we will get a point A, and again it is reflected, and again it is reflected. So it is saying that the wavefront must remain in phase after the wavefront transverses the fiber twice and is reflected twice. So once it is reflected twice, its phase remains same. If propagating wavefronts are not in phase, they eventually disappear, and wavefronts disappear because of destructive interferences. Okay, and some waves are in phase and some others are in out of phase. Once in phase wavefronts comes with out of phase wavefronts, they will cancel out because of destructive interference. This interference is the reason why only finite number of modes are propagating along the fiber. Okay. So next we will discuss about modes, and it is shown a figure, and it is this figure shows various modes also. We can say a set of guided electromagnetic waves is called the modes of an optical fiber, and in the case of you might have studied Maxwell's equation in Maxwell's equation in the case of what is in microwave devices. So Maxwell's equation describes electromagnetic waves or modes having two components. What are those components? Electric field and magnetic field, and it may be represented in terms of E of x, y, z and H of x, y, z. Sometimes we are using the notation E of r theta phi and H of r theta phi. Okay, that means E and H are right angles to each other. We know that electric field vector and magnetic field vectors are right angles to each other, so we can say that they are transverse in nature. And the modes traveling in optical fibers are also transverse. And here it is shown a figure, and in that figure we are showing the electric field patterns only. That means the transverse electric field is shown, that is T. T is transverse electric field pattern. Mode field patterns are shown. That means the mode field patterns shown in the figure are transverse electric in nature, that is T in nature. That means here in T mode, what is the meaning? Electric field is perpendicular to the direction of propagation. Here the direction of propagation is also shown, and it is seen that from the figure electric field vectors are perpendicular to the direction of propagation. And the magnetic field, that means the magnetic field is in the direction of propagation. Okay, electric field is perpendicular to the direction of propagation, and magnetic field is in the direction of propagation. Then we can say that it is a TE mode, but there is also another mode, that is TM mode. In TM mode, magnetic field is perpendicular to the direction of propagation, and the electric field is in the direction of propagation. So that is the difference between TE mode and TM mode, and here we are interested in TE mode. And here the figure also shows the order of each mode. Here it is indicated that TE0, TE1, TE2, and these are indicating the order. Okay, 0, 1, 2, etc. represents the order of the mode, and the order of each mode is indicated by the number of field maxima within the core of the fiber. So we can define the order as 0, and that means the field maxima. Actually, the order of each mode is indicated by the number of field maxima within the core of the fiber. Okay, and 0 represents the number of field maxima. Actually the order is 0, but the number of field maxima in that is 1. Okay, you can clearly see in the figure that inside the core there is a maximum point for T0 mode. Okay, there is one maximum point, so it is represented by T0. That means even when the order is 0, that means there will be one field maxima at the center of the core. Okay, that means T0 mode has a one field maxima at the center of the core, and you can also see that, and that field maxima decays towards the core cladding boundary. Okay, and that field maxima is decreasing towards the core cladding boundary. And it is also seen that there is a reference line is given for the analysis purpose, and that electric field pattern does not cross at any point of this reference line. Okay, so T0 is the fundamental mode and lowest order standing wave. Okay, and we can also say that this T0 mode, that is the fundamental mode, that is also a lower order mode since its order is 0. So that penetrate the cladding slightly. And we can also see in the figure that in this electric field is concentrated near the center of the fiber, because its field maxima is at the center of the fiber. So these all quantities we can see in the figure of T0. Okay, also there are other modes also, T1 mode, T2 and T3, etc. And we can also see in case of T1 mode there are two field maxima. Okay, there are two field maxima at the center of the core. Core is given in the core is shown in the diagram, and there are two field maxima in the case of T1 mode. And also it is also seen that electric field pattern crosses the reference at one point. Okay, it crosses the reference at one point. So we representing T1 and the order will be 2. Okay, so for T1 the order of the mode will be 2, and we can also see T2 mode. In T2 mode we can see that the field maxima patterns, there are three field maxima, electric field maxima inside the core. There are three field maxima inside the core. If you are drawing a reference line, and two field maxima are left to the reference line, and one field maxima is right to the reference line. And also we can also see that there are two crossing points with the reference line, and these field patterns are crossing 2 points of the reference line. So we can represent TE2, and the order of the mode is 2, and that means 3 field maxima are there. And the next figure T3 mode, and in this case there are 3 field maxima inside the core, and it is crossing 3 points. Sorry, there are 4 field maxima. Sorry, there are 4 field maxima inside the core, and it is crossing. It is crossing 3 points of the reference line. So its order is 3. So it is represented TE3 mode. And in this all these figures we can see that modes are not confined to the core of the fiber. Okay, and once it is field patterns comes to the edge of core cladding interface, it decays. Okay, modes extends partially into the, so we can say that modes extend partially into the cladding material. Okay, that means modes are not confined to the core of the fiber, and this modes extends partially into the cladding material. So there will be cladding modes also, and this is due to refracted rays. Okay, there will be, that means there is a core mode, and there is a cladding mode due to the confinement of the field patterns to the cladding region. Okay, usually when the number of field maxima increases, the order of the mode is also increases. And generally modes with more than a few field maxima are referred to as higher order modes. So sometimes the field maxima, there may be 5 or 10 5 to 10 field maxima, so these comes to the category of higher order modes. Okay. In higher order modes, we can see that the electrical and magnetic fields are distributed more towards the outer edges of the fiber. And here also in T3, electric field vector and magnetic field vector are going into cladding region also. So we can say that in higher order modes, some of the rays will be lost, or some of the waves will be lost, or light rays will be lost in the cladding region. Okay. And there also here we discussed about a single order lower order mode and higher order mode. And also there is some other mode like leaky modes, and usually leaky modes leaky modes will not helps in propagation, and they will vanish as the light propagates through the core of the fiber. Okay. And for a mode to remain bound inside the core of the fiber, or for a mode to remain bound, there is some condition, and that is expressed in terms of a propagation constant beta. And we can say that that condition is, for a mode to remain bound, if the propagation constant beta follows the following condition, that is the condition is that 2 pi n2 divided by lambda less than beta less than 2 pi n1 by lambda. That means the propagation constant value should lies between 2 pi n2 divided by lambda and 2 pi n1 divided by lambda. Okay. Once the propagation constant value beta is less than 2 pi n2 by lambda, it will disappear. That means that mode will vanishes to cladding region. Okay. That's the thing. So you should remember that relationship also. And that is the condition for a mode to be bound inside the core is that propagation constant beta should be higher than that of 2 pi n2 divided by lambda, and also propagation constant should be less than that of 2 pi n1 divided by lambda. That is an important relationship. And once propagation constant is less than that of 2 pi n2 divided by lambda, that mode will appear into the cladding region. Okay, that will be refracted out. Okay, the mode will not be, that means the mode will not bound to the core region. So that's all about mode theory.